Simulation nodes is a super powerful tool that was added in Blender version 3.6 onwards. In this video, we're going to use the power of simulation nodes to create this particular animation. It's not going to be looping, but it's going to use a lot of math and is going to be created completely procedurally. So I'm going to try to explain exactly why we do what we do and all of the math behind it, such that you can understand how simulation nodes works and you can use its capabilities to create your own stunning renders within Blender. And with that, let's actually learn how you can create this in Blender yourself. In the default scene, since simulation nodes is a part of geometry nodes, we're going to bring our cursor to the junction of these two windows, click and drag up to create a new window, and then change it from the 3D viewport to the geometry node editor. Then we can press this plus button to create a new geometry node tree to actually start working with the geometry nodes. One thing that's necessary to know before you actually jump into simulation nodes is the way that geometry nodes is evaluated. And essentially all you should know is that it's always evaluated from the output side towards the input side, which means it's going to first try to give a geometry output, and obviously it has to figure out what it's getting this from. So it's going to go to the left, see whatever nodes are there, and for those nodes, whatever's connected to it is going to be evaluated. So it keeps traveling down the chain from the output side towards the input side. Hence, if you use some sort of a information node like position or any other attributes, it'll always give you the position of whatever's there just to its right or whatever it's being connected into. And with that, we have the base knowledge of the working of geometry nodes, and we can actually start off creating this. Now, the group input is a cube, but we want to create our own cube so that we can deal with the size. So we'll press X and delete the group input, and then press Shift A and search for a cube and plug it into the group output. Now we can shift, select, and drag to select all of the X, Y, and Z axes, and then type in a number like 5 so that we have a much larger cube. Now we want to use a bunch of points for the simulation, and so we want to distribute these points within this cube. Now the easiest way to do that is by pressing Shift A and searching for a mesh to volume node, and then distributing the points within this volume. Now another thing is that you can actually see how long all of the operations take by coming up to this overlays panel and switching on timings. And if you actually play around with these settings, the actual time it takes to evaluate increases quite a bit. However, if we use simulation nodes, we don't need to worry about how detailed these nodes are because they're going to be evaluated only once. Unlike other scenarios, they're evaluated only on frame 1, after which they are no longer evaluated. So even if they are very heavy, it's not too much of an issue. However, we don't require that much of heaviness in this particular animation. So we're going to go ahead and reduce the voxel amount down to 2. And we're also going to just decrease the interior bandwidth to 0 or whatever the minimum values are, so that essentially we actually get a volume cube of size 5. If we increase the exterior bandwidth, the volume cube is going to be larger than 5, and that's all right because we actually want a sphere and we're going to cut it off using math in a while. So for now, I'll keep the exterior bandwidth at 0.2 and we'll move on to actually distributing the points within this volume. I'll press Shift A and search for a distribute points in volume node and plug that in to get all of these points distributed within the volume. So now we actually want to convert this cube distribution into a spherical distribution, and that means all we have to do is just delete all of the points that are outside a sphere present within this particular distribution. Hence, we have to figure out which points have to be deleted. Now to do that, we can actually find the position of every single one of these points, and if we actually use the position attribute, we are going to get a vector that goes from the origin to that point. So if we want to find the position of this particular point, we're going to be returned with a vector that goes from the origin to that point. Similarly, if you want the position of this point, we're going to get vector that comes from the origin to that point. And essentially, if we find out the length of this vector, we can figure out whether or not it's going to be lying within the sphere that we select. So we can go ahead and press Shift A and search for a position node as well as a vector math node. So we'll press Shift A and search for vector math, and we're going to convert this vector math from add to length so that we can find out the length of the position vector. So we plug it in and the output is going to be the length. Now we have to compare the length with the length or the radius of the sphere that we create. So we press Shift A and search for a compare node and plug the value into the compare node. Now we want to delete all the points that are greater than the radius. So we're going to keep it at greater than itself, but we have to actually define the radius of our imaginary bounding box. We can do that by hard coding the value here, but I'm going to use that value for the simulations later on. So I'm just going to create a separate value node and use that. Also, to label it, you can go to the node tab over here. If this side panel is not present, you can tap N to bring it out and just label it as bounding box radius. And so now we know that that is the bounding box radius. Now we're going to increase the value to something like 5 and plug that into the compare node. Now we're actually going to get a true or false value from this greater than to see all the points that are actually outside the bounding box or the bounding sphere. So I'll actually call it bounding sphere, not bounding box, and we can just go ahead and delete those. So we'll press Shift A and search for a delete geometry node, plug that in after the distribute points and volume, and use this result as the selection. So that way all the points outside that radius are deleted and we get a spherical distribution of points. Remember, if you don't actually see a spherical distribution, it might be because of the way you set up your voxel amount and the exterior bandwidth. So for example, if I reduce the exterior bandwidth and I increase the voxel amount to something like 64, we actually get a cube itself and not a sphere because the distribution of the volume is much smaller. So we can always just play around with the exterior bandwidth till we make sure that it's just points within the bounding box and it's actually a spherical distribution. So now that we have all of these spheres or points present within this sphere, we have to actually define what the radius for every single one of these points are going to be. To do that, after the delete geometry, we can search for a set point radius node, plug that in, and by default the value is 0.05, but I want the spheres to be slightly larger, so I'm going to use another value node to control that. So I'll select this value node, press Shift D, bring it down, change the label to particle radius, and I'll give it a value of maybe 0.5, and I'll just plug that back into my sets point radius node. So now we have all of our so-called spheres, and these spheres are what we're going to use to actually simulate the motion. Now there's three separate simulations that I want to actually do. The first simulation is to see spheres that are colliding with themselves. So for example, this sphere is clearly colliding with this particular sphere. So I want them to repel and eventually stop colliding with each other. The second thing that I want to do is actually create motion such that once I get them to stop colliding, the speed at which they were pushed away should get them to continue moving in that particular motion itself for at least a while. And finally, the third simulation that I want is for it to actually interact with the bounding box as well as an external sphere. So we'll go ahead with that step by step and we'll see exactly why we're doing what we're doing when we do it. So we'll press Shift A and search for a simulation zone node, and that brings in this particular purple gray area, which is the actual loop. So anything within this purple region is actually going to loop repeatedly. So we'll bring this points into the geometry and this into the output geometry. So now whatever we do within this region is going to happen on every single frame. So the first thing that we wanted to do was actually see if there's any self collision, and we want to separate these out. So we have to figure out how we're going to do that. And it's actually fairly simple. We already set a radius for these particles. If two particles are present close to each other such that the distance between them is less than twice the radius, it implies that they are colliding and they should move apart. So we can go ahead and figure that out. We'll press Shift A and search for a position node that we get the position of every particle, and we need to figure out the closest particle present to it. So to find out the closest particle, we can search for an index of nearest node, and this will simply give us the index of the nearest object that is present closest to the position that we supply over here. If we take this position, plug it in, we're going to get the output as the index of the closest point. So for example, this particular point, while being evaluated, will probably give the index of this particular point that's present right next to it. So we have to actually evaluate the position of whatever particle is present at that index. So we'll press Shift A and search for an evaluate at index node, and we'll just plug this index into the index. Now we need to evaluate the position, and the position is a vector. So we'll change this from float to vector and plug this position into the value. Now we have the position of the sphere that's being evaluated, and we have the position of its nearest neighbor. To find out the distance between them, we can actually just use the distance node, but we're going to require a vector between them later on anyway to calculate in which direction they should move. So we'll do that separately, although you could do that in one swell swoop, but I think it's easier to understand if we do it separately. So first we'll evaluate the distance between them. For that, we'll press Shift A and search for a vector math node and change it from add to distance, and we'll just use the distance between the position of the original point and the position of the nearest neighbor. Now, if this distance is lesser than twice the particle radius plus some tolerance if you want, then they should move. So I'm actually going to take this particle radius and plug that into a compare node so that we can compare the distance. So we'll press Shift and search for a compare node, change it to less than because we want to see if the distance is lesser than the length it should be. Only then should they move apart. We take this value and plug it in, but we don't require just the value, we require twice the value. So I'll press Shift A and search for a math node, and I'll change it from add to multiply, and I'll multiply it by 2. So that way we we get twice the radius. Now, if you want some tolerance, you can press Shift A and search for another math node and just add that in. So I'm going to have a very small tolerance, maybe a tolerance of 0.01, which means that even if they're really close to each other, within a value of 0.01 itself, they will still move apart and they don't necessarily need to actually touch to create the repulsion. Now, if it's lesser than this, we want them to move away. So how do we get them to move? We can get them to move by using a set position node. So I'll go ahead and press Shift A and search for a set position node and plug that in right here. Now we have to find out what the actual position has to be changed. For that, we have to actually subtract the position of these two nodes. Remember, if we have 2 points, let's say point A and point B, the position node from the origin will give us this vector and this vector. If we subtract, or we want to find A minus B, this resultant is going to be a vector that goes from B to A. So this vector is A minus B. So whichever number is being subtracted initially, so if it's A minus B, it's going to point towards A. If we had instead B minus A, then the vector would have gone from A to B like that. And if we have two particles, let's say two particles like this, obviously we want the particle present to the left to move towards the direction that it's at, and the particle to the right to move towards its own direction. So that's why we always want these to move towards the direction of the difference between the two position vectors. So we'll go ahead and just move these a bit lower and then press Shift A and search for a vector math node and change it from add to subtract. Now, since we want them to move towards their own position, we have to have the original position as the first vector. So this goes into the first vector, and the position of the nearest neighbor is going to go in as the second vector. And now if we just put this vector into the position, we don't quite get what we want because we have to actually use the selection that we created over here, which is all the particles that are actually colliding with themselves. So we plug this result into the selection, and then we can actually play the simulation to see how everything just gets pushed right to the center, except for the few that were not initially intersecting with any other particle. So evidently we need to fix a few things. The reason this is happening is because the actual vector is mainly for the direction, and we don't actually need to set the position. We want it to remain in the original position and just start moving in that direction. So to move it in that direction, we have to change this from position to offset. And now we can go back and then just play the animation, and you should see that everything keeps moving until there's no more intersections. So if we actually play the simulation again, we can see that whichever particle was intersecting with a neighboring particle will eventually move and keep moving until it reaches a situation where it is no longer interacting with any other particle. That's how we prevent self collisions. So the next thing that we have to do is actually get these to continue moving in the direction that they were moving to prevent the collisions. And to do that, we need another set position node, and we need to figure out the velocity. So essentially, velocity is always position final minus the initial position, or the final position minus the initial position divided by time. So this is velocity per se. Now, if we use the unit of time as frames itself and not seconds, and we're evaluating this for every single frame, so that means the denominator is always 1. The velocity is essentially going to be the final position minus the initial position. Hopefully that makes sense to everybody. And if you want the units, it would be meters per frame. But yeah, this is what we have to evaluate. So to find out the velocity, we're going to have to find the position before the actual simulation and the position after the simulation. So we have the initial position present in the geometry over here, and we have the final position right over here. But the actual position node will always give whatever it's connected to towards the right. So that's why if we want to find out the position over here, we have to get a node just before it and actually capture the value and keep it in a separate folder node. So that is actually the capture attribute node. We can use this capture attribute node to actually capture the position of whatever's happening just before we do any operation. So the operation that we want to do is we want it to actually move. So movement is again done by a set position node. So I'll just take this set position and press Shift D and bring it here. Now I want to capture the attribute. So I'm going to take this geometry, plug that in here, and plug this out here. Next, I want the position to be captured. So I'll search for a position node, and I'll change this from float to vector because position is a vector. Plug this in, and now the original position is stored from this particular socket. Now I need to actually evaluate the final position, and the final position comes from anything that's connected here. So I'll go ahead and press Shift A and search for a position node, and I'm going to subtract these two values. So I'll press Shift A and search for a vector math node and I'll search for subtract. Now remember, velocity is final position minus the initial position that's stored over here, and this output is the velocity, so we're just gonna plug that into this simulation output. So that way this position will be giving us the value of the position right at the output. So now the socket is called vector for now, but I don't want it to be called vector. I want it to be called velocity. So I'm just going to select it and then change the name to velocity. Now this velocity is automatically going to be fed back into the simulation input because that's how geometry nodes works. Anything that you send out will have to come right back into the start. And now we're going to use this velocity to actually set position. So I'm just going to plug this velocity into the offset so that it moves by that amount. And then to actually refresh this scene, you have to go back to frame 0 and then press play. Now you see they're all going to move and they keep moving. Obviously in the real world, they don't keep moving because there's friction present. So I'm going to have to add in some friction, which is just going to be some damping. So to damp it, I'll again go back to frame 0, press Shift A, search for a vector math node, and I'm going to change it from add to scale because I want to damp it by the same amount on all of the axes. If you're doing anything by the same value on all 3 of the axes, you can always just scale it down. So I'm going to plug this velocity into this vector and I'm going to change the scale down to something like 0.9 so that every frame it becomes 90% of the original speed that it had, unless of course it has some other interactions going on that causes it to speed up again. However, we'll bring this into the offset, and now if I play the animation, you can see that they eventually slow down and stop after some point. So that is the power of simulation nodes. We're actually able to simulate these points interacting with each other, slowing down and stopping. With that, we come to our next situation or problem, which is they don't respect the bounds of the imaginary sphere that we created. We want it such that if it goes out of the imaginary sphere, it has to get pulled back in. Hence, we can just go ahead and simulate that section of the simulation now. To do that, we'll just go ahead and take this, we'll bring it to the side so that we have more space to work with. And now we'll sit and figure out what we have to do. First, we have to evaluate the position of these points and check whether they are outside the radius. If they're outside the radius, we have to set their position to come back in. I think that's actually fairly simple to do. So we've already figured out how we can check whether it's within the given radius by using this particular node group. So we find the position, we check its length, and then check if it's greater than the radius. However, we just have one extra step, which is bringing it back in. So let's go ahead and do that. We'll take the position, length, and the greater than node, and then press Shift D and bring it here. Now again, for the greater than, we need to make sure that it's greater than the bounding box that we created. So we'll take this bounding box value and plug that into the greater than node. And then we have to actually set position again. So we'll take this set position node, press Shift D to duplicate it and bring it here. Now for these that are present outside, they have to come back in. So instead of actually pushing them towards a particular direction, we can actually set their position to just be a bit closer to the origin. And in the next frame, it'll check if it is reached within the sphere. If it hasn't reached within the sphere, it's going to go a bit closer towards the origin. And that's actually very simple to do, which is we have the position vector and we just have to scale it down by a little bit and then set that as the new position of these particles. So we'll take this position vector, search for a vector math node, change it from add to scale, and just scale it down by maybe 0.95 and then plug that into the position. Now if I go back to frame 0 and play it, you can see that if anything's coming out of the bounding box, it's getting pushed right back in, which is exactly what we wanted. And that is just another great feature of geometry nodes. Next, we can actually create the simulation of another object interacting with all of these particles. So we first have to add in that new object. So I'll go back to frame 0, and if there are keyframes being created, just select them and press X delete because we don't actually need any of those keyframes as of now. Now we'll press Shift A and search for a mesh icosphere. I'll expand it and just increase the subdivisions to something like 5, and I'll go to object, shade smooth, and I will scale it up by maybe 2 units. Now remember, the icosphere has a radius that's always equal to the scale. If you actually grab it on the y-axis and then press 1 or 3 to go into the side or front views, you actually get the grid, and you can see that from the center to the side, it's actually 2 units because we scaled it up by 2, which means the radius of this sphere is always going to be equal to the scale of this particular sphere. That's going to be useful in our geometry node tree. Now let's select our geometry node object and take this icosphere, change the name to collision object, and we can change the cube to simulation object, and then go ahead and just drag this collision object into the geometry node over here. Now the first thing is that this sphere is going to keep changing position over the course of the animation, so I have to change it from original to relative. objective to get the right locations. Next, we have to think about how we're going to get this sphere to interact with these particles. And that's actually very simple to do. These particles should never be within the radius of the sphere. If they are within the radius of the sphere, they have to get pushed outward. So it's going to be pretty much the same thing again. First, we have to figure out whether a particle is present within the radius of the sphere, including its own radius. So just like before, we have to actually add in the radius of the sphere plus the particle radius plus some tolerance if we want. Hence, remember the radius of this sphere was the scale of the object. So I'll press Shift A and search for a math node, plug the scale into the first value and the actual radius of the particles into the second value. So I'm just going to drag it from here and then go ahead and plug it into the add value over here. Next, I want to actually add some tolerance. So I'll take this add value, press Shift D, and then just add in a value, maybe a tolerance of 0.2. Now this is giving me what the minimum length should be between this object and the point. So I have the location of this object. I need the location of every point. I'll press Shift A and search for a position node. And now I have to compare these two. So to compare them, I'm going to use a vector math node because these are vectors, and I'll just search for the distance between them. So I can plug this in, and this distance has to always be lesser than this output. If it is greater than this output, we actually do the set position. So we're going to need a greater than node, which is actually a compare node. So we compare these two values, and this is going to go into the selection of another set position node. So again, shift this to the side, take this set position, Shift D, bring it in here, and this is going to be our selection. Now we actually have to find out how we move it, and the movement is going to be very similar to how we did the movement for these particles, but here we're just going to be setting the position instead of actually using an offset. How we're going to do that is first figuring out the position that it should be at. For that, I have to find, as usual, the vector between the point and the object, which is actually done by subtracting. I'll press Shift A and search for a vector math node and change it from add to subtract. Now I'll plug the position into the first vector and the location in the second vector. Since we're subtracting the position of the particle from the position of the sphere, which means we're getting particle minus sphere, we are getting a vector that's actually going from the sphere to the particle, and that's exactly what we want. However, we now need to figure out what the length of this vector should be so that we can put this point just outside the sphere, assuming that it's inside already. If it's outside, we do nothing, and that we figured out using this particular selection that we've used. But if it's inside, so suppose the point was present over here, we get a vector like this, and we need to find out the direction, and then we have to find out the length of the vector necessary to push it out to out here. Now we already have the direction over here, but now we need to figure out the length. So to find out the length, we can first normalize it and then scale it by the necessary amount. So normalizing will just change this vector's length to 1, irrespective of whether it's greater than 1 or less than 1. So I'll press Shift A and search for a normalized node, which is not present directly. We have to use a vector math node. So I'll search for a vector math and change it from add to normalize, and then just plug this vector in. So now we have a vector of unit 1 that's pointed in the right direction, but we need it to be equal to the length of this sphere plus the length of those tiny spheres. So let's say we have the sphere here. We need this length to be this plus this, and this is how it should be. Right now we have the length only as 1 unit, so something like that. So to scale it up, we can just use a scale node, which is again a vector math node set to scale. So just duplicate this, change it this time from normalized to scale, and we're going to scale it up by the radius of this sphere plus the radius of the smaller sphere. So again, we have the radius using the scale over here, and we have the smaller sphere present over here, and we have the summation of those two plus the tolerance output right here. So we'll just use this value and plug that into the scale. Now we have a vector as the output of this that's from the origin pointing towards the right direction and is also of the right size, but it's not present in the right location. To get it to the right location, we need it to get to the position of the sphere, and to bring it to the position of the sphere, all we have to do is just add in the location of the sphere. So again, take the scale node, press Shift D and bring it out here and change it from scale to add, plug this vector in here, and for the second vector, take the location of the sphere. So take this location, plug that in here, and plug this vector into the position to see what's happening. Right now everything is getting attracted to the sphere, which means our selection is wrong. And yes, obviously our selection is wrong because if the length is lesser than this value, that means it is present inside and it should get pushed out. Hence, this should work, or the position should be set only if it's less than, not greater than. So we'll change this from greater than to less than, and then play the animation, and this is what we currently have. We can then select our sphere and just move it around, and we can't really tell the interaction of these particles with the sphere because the particles are moving way too much by themselves. So let's first reduce that. The way we can reduce that is by using this subtract value over here, which was causing the self interactions. Instead of just subtracting it, we can actually reduce the effect effect of this subtract node by scaling it down by using a vector math node and changing it from add to scale. Now we'll scale it down by a value of something really small, maybe 0.1. And then if we play the animation, it should have been moving lesser, but it is going straight to the center and struggling there. We need to figure out why that's happening. So let's troubleshoot this. Essentially, this subtract node is giving you a vector that's going from one point to another. And so it's giving you the right direction. It's not giving you the right position. And that's why we're using the offset value. And if we scale that down, it should be moving by a lesser amount. So this is right, but evidently something is wrong. All right, so after quite a lot of searching, I figured out that my greater than node over here was not plugged into the socket. So if we just plug that into the socket and then go back to frame 0 and play the animation, we should get lesser motion. Yes, this is working absolutely fine. So yeah, I don't know how that got disconnected, but a single disconnection over here caused quite a lot of searching because I've been trying to figure out what was wrong over here because it should have worked. The logic was absolutely fine. So troubleshooting and checking other areas of the mesh is very important. Don't just focus on the area that you just made changes to because you might have accidentally made changes somewhere else as well. So now we have these small jiggling motions. Let's go back to frame 0, then select our sphere and just push it around. Now you can see the particles are moving around the sphere, which is exactly what we want. Now we can actually push the sphere through and all these particles get pushed around just as well. If you can actually move the sphere around, and this is what you get. So that means that our simulation is working absolutely right. We're able to interact with the particles and they're all moving. The last thing that we have to do in the simulation nodes or the geometry nodes is actually set all of the original objects. So the first thing is that if you actually switch on rendered view and switch off overlays, all of these particles disappear because they're just points and not actual geometry. So to actually create real geometry, we have to press Shift and search for an instance on point node and plug that in before the group output. For the instance, we'll use an icosphere so that we can control the subdivisions fairly easily. So plug the mesh into the instance and increase the subdivisions to something like 3. Next, we want this radius to be the radius of the sphere. So we'll go back to this point radius value over here and just plug this into the icosphere radius. And now it actually seems like these icospheres are struggling to fit inside. Next, I'm going to increase the subdivisions to 4 and actually set shade smooth so that we don't see these individual faces. And you can see that there still is a little bit of overlap. So they do push away, as you can see over here. But if you want them to push away even faster, you can actually create substeps to the animation, which is what we actually do for physics simulations, which is between every frame there can be multiple calculations, but I'll deal with that in a future video, so stay tuned for that one. And till then, let's just go ahead and press set shade smooth and plug that in. Of course, you could also increase the tolerance value that we had kept in all of these regions, this tiny little add that we had. So over here, if we actually increase this add value from 0.01 to maybe 0.1 and then just play the animation, we might not get situations where they actually collide like that for so long. Even if they do collide like this is colliding, within a frame or 2 they should detach, which is exactly what we want. It's good enough for the animation that we're doing as of now. So now once we have them set to shade smooth, we can go ahead and set the material as well, which is the last thing that we have to do. So we'll press Shift and search for a set material node and plug that in. Now we'll just go ahead and choose the default material, which is good enough. Next, we can select our collision object, go to the material properties, add in a new material and give that name to collision, and then we can start the actual animation. Before that, we'll set all of our defaults. So we'll go to our render properties, switch on ambient occlusion, increase the distance all the way to something like 5, increase the factor to something like 5 as well, and then switch on bloom and screen space reflections. Then we'll go to the output properties, change the frame rate to 30 frames per second, and frame is going to be 150 so that it's a 5-second long animation. Output folder can be wherever you want it to be, and file format is FFmpeg video. Then I simply want this sphere to go through this object a few times. The way I'm going to do that is by making it follow a Bezier circle. So I'll press Shift A and search for a curved circle. Just scale the curved circle up a bit, then press Tab to go into edit mode, select 2 opposite vertices and then press X, delete the vertices, then select these 2 vertices, scale them on the X-axis by quite a bit, and then just select one of them and rotate it on the Y-axis by 180 degrees to create like this infinity shape. And maybe I can just scale it up on the Y-axis a little bit as well as the X-axis a little bit. Then press Tab to go back into object mode, go to the actual curve properties, increase the resolution to something like 100 so that it's very smooth, and then select my collision object, go to the constraint properties over here, add in a follow path constraint and also press Alt G to clear location, and for the target choose the Bezier circle. Now this animation is not going to be a looping animation, but I'll just make it go through one loop. So on frame 1 I'll hover over the offset and press I, and on frame 150 maybe I'll make it go through 2 loops. So I'll make the offset 200 and then press I. Now down here I'll press T linear, and then I'll just play the animation, and you can see this ball move and all these smaller spheres present inside also moving along with the ball. And that's all there is for the animation. Maybe I'll animate the camera as well, which I'll put in for the scene setup. So for the scene setup, I'll press Shift A and search for an empty plane axis and just scale it up. Then I'll select my camera, press Alt G to clear location, Alt R to clear rotation, or X 90 to rotate it on the Y axis or the X axis by 90 degrees. And then I'll press GY and just bring it back. Then once I have it here, I'm just going to grab it on the Z axis to move it up a bit, and then rotate it on the X axis to make it point downward. Then I'll press 0 on my numpad to go into the camera view, and I can't really see most of it. So I can either increase the focal length of the camera by bringing it down to 25, or I can just grab my camera on the Y axis and just push it back a little bit. Once I'm happy with the positioning of the camera, I can shift select the empty and then press Ctrl P and set parent to object. Now on frame 0 or frame 1, I see that this sphere actually collides with the particles on frame 15. So on frame 1, I'll just select the empty. I'll rotate it on the Z axis by a slight value, so maybe 15, and then press I rotation. Then on frame 150, I'll just press R Z 360, but I want it to be in the negative direction, so minus 360, and then press I rotation. And then down here, I'll press T linear. So now when I actually play the animation, you can see the sphere going through these smaller spheres and coming out, which is good enough for the animation that I want. Next up, I can start the actual texturing. So for that, I'll change my viewport display to render, and I could keep this light. It looks good actually, but I'm gonna go ahead and just select it and press delete to remove it. Then I'm gonna go to my world properties, increase the background all the way to white, after which I want the background to actually seem black. So I'm going to change my geometry node editor to the shader editor and change from object to world. In the world, I'm just going to duplicate the background node by pressing Shift D and then searching for a mixed shader node and plugging it in after the background. So just plug the second background in as well. And I'm going to change the second background color all the way to black. Now for the actual factor, I'm going to use a light path node and take the is camera ray output into the factor. So this way the camera sees a black background, but the sphere sees the white background, which is exactly what I wanted. Then I can start off with the texturing for the individual sphere and the smaller spheres. So I'll change from the world to the object, and I'll select my geometry node object that has the default material attached to it. Now for these materials, all I'm going to do is just increase the metallicness all the way to 1 and maybe reduce the roughness down to 0.4. Then for my collision sphere, again, I'm going to increase the metallicness all the way to 1. I'll keep the roughness at 0.5, but I'll just reduce or increase the base color to this nice bluish color, and that should be all right. And this is the animation that we have. So with that, if you're happy with the way everything looks, all you have to do is press render animation. Hopefully you learned something from that video. I know it was a bit more math oriented and a little bit more complex than what we generally do. I tried my best to explain why we're using the vectors that we are using and how we're going about creating this particular animation, but I'm sure that there will be people that weren't able to follow along because it was a bit convoluted. So I will create many more such effects using simulation nodes, and hopefully with multiple tutorials, I will get better at teaching and explaining how you can implement simulation nodes and geometry nodes to create amazing effects. And with that, all of you will also be able to create stunning animations and simulation using the same. Until the next video comes out tomorrow, thank you so much for watching, because the watch time really helps me. And until the next video comes out tomorrow, keep creating and stay creative.